Hi, welcome to our 5th training session, where we will demonstrate how to implement a precise date and time clock using the on-chip RTC block in LPC 2148. Any embedded system project involves 3 important steps. The first step, we select embedded C as our programming language. The second step, LPC 2148 based evaluation board, and the LC module. Programs written in C are readable and easy to debug. To debug embedded C program on the PC, we use a simulator. We use a Jaguar debugger to download and test the program running on the target hardware. The real-time counter block maintains system clock and calendar function. The real-time counter can be divided into 4 major blocks. The first block is the reference clock divider block. This block is responsible for generating a precise 1-second clock pulse. The second block is the time counter block. The registers in the time counter block maintains proper clock and calendar information. The clock maintains time information for the day, while the calendar maintains date information for the month of the year. The third block is the alarm registers. The alarm function provides match registers for time and date variables. The last block is the interrupt block. We can generate an interrupt when a time or date register increments, or when alarm register matches the current time and date. The interrupt location register identifies the source of the interrupt, which could be because of time register increments, or when alarm register matches. The real-time clock, or the RTC, is a set of counters for measuring time. RTC requires an accurate 1-second clock pulse to maintain time and date functions. Please note, a 15-stage binary counter has a maximum value of 32,768. The 15-stage binary counter is named as clock tick counter. We can generate this precise 32.768 kHz clock using an external quartz oscillator, or use the internal peripheral clock and divide it using a pre-scale registers. The crossware wizard helps us by providing the accurate values to be loaded in the integer and fraction register, and generates the 32.768 kHz clock output. The clock control register, CCR, is a 5-bit register and controls the clock divider circuit. The first bit, when set, enables the counting operation of the time registers. The second bit resets the clock tick count register, while the fourth bit controls the clock source. If this bit is set, the external quartz oscillator drives the clock tick counter, else the peripheral clock with the pre-scale registers drives the clock tick counter. The 8 time count registers are responsible to maintain time and date information. The minute and second time register is 6-bit wide and resets when it reaches a value 59, while the hour time register is 5-bit wide and can count to a maximum value of 23. The month time register is only 4-bit wide and the maximum count is 12. The year time register is 12-bit wide and can have a maximum value of 4095. All these time registers can be read and written for updating time information. There is also consolidated time registers, wherein by reading only 3 register, the software can get complete time and date information. The alarm register are a set of 8 registers, which holds a precise time and date information in the future. The current time is compared with the future date and time, and if it matches, an interrupt can be generated. An RTC interrupt can be generated when any register in the time count block increments. The count increment interrupt register is responsible for interrupt generation in the time count block. If the bit 0 in the CIIR register is set, an interrupt will be generated every time the seconds register increments. When bit 1 in the CIIR register is set, an interrupt is generated when minute value increments. So if we need to generate an interrupt every hour, we need to set the second bit in the CIIR register. If we need to register a change in the date of the month, then we need to set bit 3 in the CIIR register. The bit 4 for day of week, bit 5 for day of year, bit 6 when month value increments, and bit 7 when year value increments. The interrupt generated because of time count block will get cleared when bit 0 in interrupt location register ILR is cleared. An RTC interrupt is also generated when the alarm register matches the count time registers. The alarm mask register allows the user to mask any alarm register for comparison. If the bit 0 in the alarm mask register is set to 1, then the second counter will not be compared with the time counter second register. If we need to set the alarm every day morning, we need to unmask or set to 0 the seconds, minutes and hours bit, and mask the remaining bits in the alarm mask register. The interrupt so generated because of the alarm block will be cleared when 1 is written to the bit 1 location in the interrupt location register. Let us start coding our fifth lab on real-time clock. We create an universal character pointer and name it as message pointer. We then create a message array named message time for displaying time in hour, minute and second format. We then create location constants using hash-defined directives. These define actual position of time values in the message for hours, minutes and second. All C program starts from main. The first step we do is to initialize the general purpose I/O ports. We then initialize out timer for a 1 microsecond interrupt. In the next function call, we initialize our LCD module. We then go ahead to initialize our real-time clock. We will be using peripheral clock to generate a 1-second tick. We initialize time in the setTime function. The program then enters into a permanent loop, displaying current time on the LCD. In our first function call, we set the I/O port directions of the first 16 pins of port 0 as output. We will be driving the 8-bit data bus and 3 control signals of the LCD module. The second function initializes the timer for generating 1 microsecond interrupt. The clock for the timer module is from the 4 MHz peripheral clock. We generate a 1 microsecond interrupt by programming the match register MR0. The crossware wizard computes the values to be loaded into the MR0 register and code for resetting the timer counter and generating interrupt. The vector interrupt controller is programmed with slot 0 for timer 0 interrupt and the vector address pointing to timer interrupt subroutine. The next function initializes the LCD module. We first create an command array named CMD8 which has all the commands written to the LCD controller. These commands resets the LCD module to work in 8-bit mode and 2 lines of display. The LCD pointer is initialized to the first location in the command array. The pointer is incremented until the end of array is reached. In the next function, we will program the RTC block. Here the first step is to select the peripheral clock for generating the 32.768 kHz clock. The crossware wizard configures the pre-scaler register by providing the values for the integer and fraction register. Then we go ahead to enable counting by setting the clock enable bit in the clock control register. The next function loads the time registers with values for second, minute and hour. We then enter an unending loop. In the first function, we home the LCD cursor by writing a value to the LCD command register. This is done by setting the RS bit low, and then go ahead to toggle the E bit by writing to IO set and IO clear registers. The next function, we read 3 time registers, the second, minute and hour registers. The last function, show message, writes the time information into the message variable, and displays the same on the LCD display. The time information is in hexadecimal. Hence we call a function to convert the hex values to printable ASCII characters. During the LCD write operation, the LCD pointer points to the time message array, and this data is then transferred to the LCD display by setting RS bit high and toggling the E bit. The LCD pointer is incremented until it hits end of array.